In the name of Almighty God, I'm Master Sankasha. Today I want to talk about a micron size, a magnonic three-port rectilinear circulator. It was written by Kevin Weber and his colleagues, which was written in Atlantic, Brest, France University. They developed a miniaturized non-reciprocal microwave technologies compatible with the integrated circuit architectures remains a critical challenge for modern information technology. Here we present the first experimental characterization of a micron-sized prototypical magnon circulator taking advantage of the chiral excitation of spin waves via nanowire gratings. We propose an original design of a circulator involving three channels of rectilinear and unidirectional spin wave beams. We demonstrate via a full three-port spin wave spectroscopy a genuine spin wave circulation between the three ports. The nerve frequency band of operation can be tuned over a broad range of frequencies, which is between 2 till 8 GHz, with both an external field of up to 100 millitesla and the dimensions of the grating specifying the wave vectors. This proposed scheme opens up possibilities for new architecture of integrated and miniaturized non-reciprocal microwave devices. Non-reciprocal components such as circulator and isolators are indispensable for protecting microwave systems for reflections, isolating radar signals, and shielding qubits in quantum architectures. However, these functionalities are not easily achieved with standard electric field devices. The current ferrite-based technologies rely on the gyrotropic nature of magnetization, remain bulky and off-chip, which limits their miniaturization into microscale electronics. This necessitates the development of alternative non-reciprocal technologies compatible with 5G up to 6G standards and integrated circuit technologies. Spin waves offer a promising platform to develop a new class of non-reciprocal devices compatible with the integrated circuit technologies thanks to various intrinsic forms of non-reciprocity cities and frequencies and amplitude. Base besides magnetics enables a scalability down to sub 100 nanometer size as well as a tunability in a broad frequency range of the microwave spectrum, making it a field of choice for miniaturizing microwave components. For so far, only theoretical efforts have been carried out to study the feasibility of a magnonic circulator based primarily on numerical simulations of complex architecture. Among these studies, the inverse design approach requires a magnetic landscape made of submicron squared pixels, while another simulation study showing unidirectional coupling schemes relies on complex multi-layer geometrical including ports on both sides of the film. While these simulations open new roads for miniaturizing circulators, they require challenging nanoscale dimensions, which poses significant challenge for both experimental realization and threshold sensitivity. Consequently, a practical micro-scale experimental demonstration of a circulator remains a critical missing link for integrated magnonic circuits. In this study, we experimentally demonstrate spin wave circulation at the micron scale on a device based on the rectilinear unidirectional spin wave beams propagating in a thin YIG film. We present results on two different prototypes showcasing genuine spin wave circulation between three ports, also allowing multi-band operation by engineering the wave vector spectra directly from the transducer dimensions. By combining this architecture with the frequency selectivity, tunability, and power dependency of spin waves, we propose a new scheme towards the miniaturization of circulators. The spin-wave circulator device shown in Figure 1, parts A and B, consists of three pairs of gold nanobar grating fabricated on top of a 55 nanometer thick yttrium iron garnet or YIG film ground via liquid phase epitaxy. This design functions as a three rectilinear beam channel architecture covering a total working area of around 100 multiplied by 100 micro square meter. Each grating acts as a chiral transducer and allowing for unidirectional transmission of spin waves between two ports. The circulation scheme is achieved by translating the pairs of grating in order to create three separate channels. Tau, which is spin waves, beams propagate rectilinearly from one port to another. The essence of the non-reciprocity used in our device is sketched in Figure 1c. It relies on the chiral excitation of spin waves in the Damon-Echbach configuration, which originates from the matching of the distribution of the microwave or state fields generated by the nanowire gratings yellow circles with the spin waves phase profile sketch with the blue and red circles respectively for right and left propagating waves as illustrated in Figure 1c. Only the wave propagating to the right hand side of the static magnetization direction M will effectively be excited accordingly with the cross product rule based on the references 13, 27, 28. Now I want to go through the first figure. Figure 1 illustrates three-port spin wave spectroscopy setup in set optical macroscopic image of the circulator prototype. This is the part A. And part B illustrates some image of the circulator. Arrows indicate the rectilinear spin wave channels and circulation direction defined by the external field polarity. And scheme C, these sections illustrates a schematic of the chiral phase matching mechanism between the microwave field distribution of the gold and nanowire yellow circles and the spin wave phase profile blue and red circles. And section D, this figure shows Fourier transfer of the excitation field from the grating showing a comb of wave vector chi n is equal to n multiplied by 2p divided by r. Insert high magnification sum of the gold nanobar transducer. The equation 1 it shows a car divided by absolute car multiplied by m divided by ms is equal to u y, y u y is a unitary vector pointing out of the plane in the direction from the field to the grating. In other words, this unidirectional excitation and thus the direction of circulations can be inverted with the polarity of the external bias field H external or also if the grating is allocated below the YIG field. Furthermore, the grating geometry provides the spectral excitation signature in the form of the coma wave vector corresponding to the integral waves of the spatial periodicity all of the nanowires, namely chi is equal to n multiplied by 2p divided by r n belongs to n0 as shown in figure 1. Section D, which the Fourier transform of the excitation field. This allows for a specific selection of several narrow frequency bands which can be adjusted with the gratings dimensions. Both investigated devices share a gold thickness of the TRU, which is a gold element, is equal to 40 nanometer. The first device shown in the scanning electron microscopy cell image in the inset of figure 1 part 2 utilize a nanobar with white is equal to 200 nanometer and periodicity is equal to 500 nanometer with an inter-transducer distance is equal to 15 micrometer. The second device, with its corresponding nanobar displayed in the inset of figure 4a, features reduced dimensions, which W is equal to 100 nanometer, O is equal to 400 nanometer, and the distance of the D is equal to 10 D is equal to 10 micrometer. In the following, we've characterized the performance of each device, demonstrating the circulation over multi-bands of frequency by engineering the wave vector spectrum with grating dimensions. The devices were characterized by the three-port spin-based spectroscopy using the Rohde and Schwarz ZNA43 vector network analyzer and the PM8 probe station shown in figure R1A, utilizing combination of EDP style dual and single Pico probes. The whole setup was calibrated via a three-port SALT short open loud tube protocol using a CS3 differential calibration substrate in order to de-embed the magnetonic signal from the rest of the setup. Figure 2 Part B displays the frequency field map of the real part of S12, S23, and S31 in linear scale, namely the transmission from the port 2 to port 1, port 3 to port 2, and port 1 to port 3, as indicated by the arrows in the figure 1b. Measurements are performed across an external field range from the -100 to +100 millitesla with a 2 millitesla increment, with the frequency was sweep from the zero point 0.1 to 6 gigahertz with 1601 steps. For this mapping, we performed single spectral scans without averaging while applying -15 decibel m of input power, and with the intermediate frequency bandwidth BWIF of 500 megahertz. Hertz, which resulted in a 66 seconds acquisition time for each frequency sweep. Owing to the weak inductive coupling, we choose to remove the parasitic baseline by performing a relative measurement of the scattering parameters. Delta S is equal to the S means minus S reference. The reference spectrum S reference was recorded at an external field. Micro zero H reference is equal to 200 millatesla, sufficiently large to display all spin waves dynamically outside of the experimental frequency range. Additionally, we show in the appendix, figure 5, part A, a typical spectra of the raw data for each port at both low and high bias field, which displays different insertion losses between each transmission channel, mainly due to the different crosstalk between the dual and single picoprobes. The transmission spectra on this device reveals the two branches corresponding respectively to the first two peaks. K0 is equal to 0 and K1 is equal to 2p divided by R is equal to 12.6 radian per micrometer, for which we expect the most efficient spin wave generation to occur from the excitation field spectral density shown in figure 1d. The latter branch K1 possesses a strong amplitude asymmetry between positive and negative fields, consistently with the cross product rule of equation 1, while the K0 branch remains largely symmetric. This difference in asymmetry between the K0 and K1 branches is expected from a more pronounced circular ellipticity of the excitation field felt by the higher wave vectors, which is requirement for the chiral coupling based on the reference 11, 13, and 28. The reciprocal spectra to S21 and S32, S13 shown in Figure 2b displays identical spin-based features with opposite applied field polarity consistently with equation 1. Additionally, Figure 2 Part C shows typical spectra at the micro zero H external is equal to 40 millitesla of all transmission parameters, namely pose delta Si and delta Sji for I and j belongs to 1 to 3 and I is not equal to j, confirming the unidirectional nature of the beams excited by the grating. See also Appendix Figure 7 for representative spectra over 400 millitesla field range. These distinct contrasts between passing and isolated ports demonstrates a genuine circulation of spin waves between all three ports. By converting our measure 3 multiplied by 3 scattering matrices into the impedance matrices as detailed in Appendix 6, we obtain the dynamic inductance spectra delta Lij. From these, we summarize in Figure 3, Part I, the field dependence of the extracted spin wave propagation properties, which includes the group velocity nu g at the attenuation length L attenuation and the corresponding relaxation time tau r is equal to L attenuation divided by nu g. These characteristics demonstrate that the property functions effectively as a combined non-reciprocal circulator and a programmable delay line. This field-dependent delay provides a powerful tool to directly investigate spin waves propagation dynamics. Experimentally, the group velocity was extracted from the time of flight measurement via g is equal to the derivative of w by x and the car is equal to d tau f, where tau f is equal to minus the derivative phi that omega based on the omega, and phi omega is the phase of the transmission spectra. It reveals an identical monotonic decrease across all transmission channels as the base field increases from the 515 meter per second at the 0 millitesla to 355 meter per second at the 100 millitesla in very good agreement with the theoretical calculation group. Velocity indicated by the dashed line derived from the dispersion-related omega rest is to the power of 2. Ka h is equal to O K omega plus omega m plus omega m to the power of 2. P multiplied by 1 minus P, where omega m is equal to gamma micro 0 ms omega is equal to gamma micro 0 h equality plus omega m tau to the power of 2 chi to the power of 2, which are to the power of 2 is equal to 2 ix divided by micro 0 ms to the power of 2. The exchange length and p is equal to 1 minus 1 minus e to the power of minus kt divided by kt, which reflects the influence of the dynamic dipolar interaction. To estimate the attenuation length L attenuation, we consider exponential decay and estimate the ratio of the mutual inductance amplitude to the absorbed part of the self-inductance Lij divided by Im Ljj is equal to exponential minus d divided by L attenuation. See also Appendix Figure 8, where d is the inter-transducer distance. This approach, which effectively de-embeds the local transducer efficiency, shows a mild increase of L attenuation with the base field yielding similar values for the channels 1 up to 2 and 2 up to 3, ranging from the 60 micrometer at low fields down to 40 micrometer at 100 millitesla, while the channel 3 up to 1 exhibits slightly reduced attenuation length ranging from the 30 micrometer to 20 micrometer respectively. This slight reduction, which is also visible in the amplitude of the transmission spectra, is likely due to the shape of our prototype, which requires a longer termination of port in order to cope lumped with port 3, resulting in additional ohmic loss compared with the two other ports. This minor weakness could be corrected with a proper microwave engineering of the scheme in order to balance all ports. Consequently, the calculated relaxation time remains remarkably stable, near 100 nanoseconds respective to 60 nanoseconds for L13 across the entire field range. These reduce demonstrate that the chosen intertransducer distance is equal to 15 micrometer is well within the attenuation length across the entire field range, confirming the observing session loss is not primarily limited by spin wave decay, but it is instead dominated by the poor impedance radiation matching at this length scale. The performance and power handling of the circulator we separately investigated for various input powers, PAE ranging from the minus 20 decibel M to 5 decibel M, and various bias field up to the 200 millimeters. Figure 3 part B depicts the power dependence maximum transmission amplitude for the carbon branch in both the passing and the blocking directions across all ports at a base field of a micro zero H external is equal to 50 millisecond below Pin is equal to minus 6 decibel m. The device behaves linearly with the relative spin wave transmission magnitude independent of the input power, pointing around minus 60 decibel. It shows a difference of more than 20 decibel between the passing and the blocking directions, with backward signals remaining indistinguishable from the experimental noise floor indirected by the dot line in the shaded region. As the power exceeds 6 decibel in, the system enters a nonlinear regime characterized by spectral distortion and amplitude reduction. These findings are consistent with the nonlinear power limiting effects observed by Deviokova and his colleagues in references 38, which is due to the onset of multitude magnonic scattering processes in YIGD films. The transition is resolved in Figure 3, Part C, which superimposes the forward transmission spectral absolute delta STL at varying power levels, while the response remains consistent up to the minus 6 decibel. Higher powers induce progressively peak compression and broadening, altering the operation of the circulator. Notably, the nonlinear threshold varies slightly, with the bias field shifting from the approximately 5 decibel m at 50 millitesla to 6 decibel m at 100 millitesla before increasing to the minus 3 decibel m at the 200 millitesla as shown in appendix figure 5. The observed increase in the nonlinear threshold qualitatively aligns with the established theories on higher powered microwave instability. However, because of all power types, return loss varies across the frequency range. This non-uniform return loss slightly disturbs the expected monotonous increase of the nonlinear threshold. To further explore the limits of frequency selectivity and the potential for the multi-band operation in magnonic circuits, we fabricated a second device with a reduced white W is equal to 100 nanometer periodically R is equal to 400 nanometer, and an inter-transducer distance D is equal to 10 micrometer refers to instead of figure 4a. The discrete wave vector allowed by the grating periodicity occurring at n is equal to n multiplied by 2p divided by r have their relative excitation strength as sampled by the single bar envelope as indicated by the red dashed line in figure 4r, and whose first zero is located at the 2p divided by w is almost equal to 62.8 radian per micrometer. By optimizing the alpha per omega ratio to the value of for an increase from the 2.5 ratio used in our first device. We effectively enhance the excitation range of this next wave vector chi2 is equal to 31.4 radian per micrometer. Physically, this geometric ratio dictates how many wave vectors peaks of the excitation come fit within the main lobe of the single bar envelope, thereby increasing the spectral weight at chi2. The experimental validation of this multi-wave vector excitation is captured in the frequency field mapping of the transmission magnitude delta SL31 shown in Figure 4 Part B in a biosphere range up to the 50 milletesla. The map clearly resolved three distinct branches: dominant and symmetry. Chi0 is equal to a zero branch alongside the non-reciprocal Chi1 and Chi2 branches. Additionally, intermediate small ripple structures also exhibiting similar non-reciprocity are visible between the Chi0 and Chi1 and corresponding to the secondary lobes of the grating's Fourier transform. We show in a figure 4 part C a typical spectra at the micro zero hx is equal to 20 millitesla for this device. Zoom around the peaks corresponding to the wave vector and Ca1, Ca2. Despite the inherent increase in the insertion losses at higher wave vector reaching 67 decibel for Ca1 and 85 decibel for Ca2. Both remain non-reciprocal with a chiral isolation of 23 decibel for Ca1 and at least 40 decibel for Ca2 above the noise floor. The residual signal observed in the isolation direction of Ca1 is likely attributed to non-complete chiral coupling or perhaps a parasitic absorption and re-emission at the intermediate portion. To finally, the frequency dependence of the propagation properties qualified three time of flight measurement tau and group velocity nu g is equal to d divided by tau are shown in figure 4 part D. We observe a distinct field dependent behavior between the two branches for the common and the tau increases from the 19 nanoseconds to 23 nanoseconds as the biosphere is sealed up to the 50 millisesla corresponding to a group velocity comparable to the one extracted for the first device. In stark contrast, the Culture branch maintains a remarkably invariant time of flight of the tau. Tau is equal to 60 nanoseconds across the same field range, which results in a constant curve velocity of is equal to 635 meters per second, greater than the one for K1. This disparity is fundamentally rooted in the underlying dispersion relation equation tuning, namely the influence of the dynamic dipolar term, and the dispersion is more pronounced at the lower wave vector K1, which makes its curvature more sensitive to the Seemann shift of the spin wave manifold. However, at the higher wave vector K2, uh, the dispersion enters a regime increasingly dominated by the quadratic exchange term, which is equal to cos to the power of 2. In this exchange active region, the dispersion slope becomes less affected by external field variation, resulting in the observed constant group velocity. This transition provides a versatile platform offering these different timing characteristics for signal routing in a miniaturized microwave architectures where both field tunable and field robust time delay can be exploited simultaneously. In summary, we have successfully implemented a comprehensive three-port spine wave spectroscopy to the characterizing the circulation of the microwave power at a micron scale. This experimental platform allows for the de-embedding of multi-channel scattering parameters, providing a rigorous verification of non-reciprocal signal routing in integral magnonic circuits. We showcase a magnonic circulator prototype based on the three pairs of non-grating acting as a three rectilinear beam channel design operating ORF working area of 100 multiplied by 100 micro square meter. This device, a first of its kind, exhibits quasi-even level of transmission amplitude and isolation greater than the 20 decibel between ports, allowing for proper microwave circulation. Further engineering of the gratings dimensions enables excitation of additional higher-order wave vector branches, offering a versatile router for the development of multi-band and frequency selectively magnetic components. These findings establish a scalable pathway for the integration of non-reciprocal technologies into high-frequency 5G, 6G architectures and cryogenic quantum systems. So the first appendix all, I want to go through the some of the pictures that I didn't review it for you. For example, figure 3 illustrates part of base field dependence of the spin wave transport properties derived from the inductances delta Lij extracted from the data in figure 2. In the passing polarity of the bias field, top section group velocity nu g, where dashed line represents theoretical calculations based on the dispersion relation equation to middle attenuation length, L attenuation, and bottom relaxation time tau R is equal to L attenuation divided by nu g. The section B power dependence of the transmission amplitude of the carbon peaks at the micro zero H external is equal to 50 millitesla in the passing solid line and isolated dashed line direction, including estimated noise floor level, shaded bands, the spectral comparison showing the spectral distortion and amplitude saturation of delta S 12 past the nonlinear threshold at minus 5 decibel m. The measurements in the B and C were acquired using a reference field of microsec 0 H reference is equal to 300 millitesla. Figure 4 illustrates the second order of the device with the reduced nanobar width W is equal to 100 nanometer, and also periodically I is equal to 400 nanometer, and the section 1 for each transfer of the excitation with an inset displaying and a SEM image of the reduced nanobar array, and section B frequency field map of delta S31 acquired using micro zero H reference is equal to 200 millitesla and minus 5 decibel m input power, revealing a second chiral vector wave vector branch called to C corresponding spectra at 10 millitesla, showing unidirectional transmission for both Ki1 and Ki2 peaks. Top real part RE is 31 and bottom magnitude absolute is 31. B field dependence of the group velocity nu g and the time of the flight T2 for both Ki1 and Ki2 peaks. So this project has received co-funding from the European Union Horizon European Research of Innovation Program under grant agreement this number. It further benefited from a government grant operated by the French National Research Agency as part of the French 2030 program reference no, and Figure 5 illustrates raw data with insertion and rejection loose. Section B power dependence at micro zero HXR is equal to calculate 100 millitesla, 200 millitesla at micro zero H reference is equal to 300 millitesla. Thank you so much for watching my tutorial video until the end. If there is any uh, simulation for this literature. You can also check my github.com/masterscript, github.com/caution script, github.com/saffron script. Today is the second day. Today is the second day in July 2026. Time is near the morning.